of LLMs.
Thank you, Challenger, for introduction and for inviting me to give a talk. It's a great pleasure to be here. And today, before we start with all these hands-on activities on LLMs, I would like to give you some very brief reminder and introduction what like history of attention, what is transformer, how we use transformer to train LLMs, and as well give you a very high-level overview of a couple of DeepMind mathematics-related projects, AlphaEvolve and ITHEA, like the latest paper published a few days ago. And if I will have time, I also will give you a brief overview of our ultra-long context and improving reasoning capabilities of transformers. Well, so actually, if we are talking about large language models, the core idea here is language modeling. So what is language modeling? And language modeling actually has a very, very simple task objective. So you have some sequence, and given this sequence, you need to predict the next element. You need to predict this probability distribution over your vocabulary of your elements, which should be the next. For me, it's a miracle how solving this very simple problem, we can get systems which can help us with such complicated stuff as mathematics. So before deep learning craze, people tried to solve this large language, language modeling task with recurrent neural networks. And here's an example of recurrent neural networks. And it works by sequentially encoding every element of your sequence. So here you have input part of the sentence, and for every word, you encode it with some hidden representation in your neural network. And then you updated this representation with every word. And essentially at the end, you make prediction on the next word. And usually with this approach, you are constrained by your current representation, like current input and previous hidden state of your network. Because in this approach, like propagation of information from the earlier step is very hard. And this was a limiting factor for language modeling, and as well as it was even more worse for sequence-to-sequence modeling. Because, for example, if we consider machine translation, which was one of the major tasks for natural language processing before our current LLM era, you see that here we have one part of your neural network which should encode your input, your sentence in your source language. And then you have decoder part, which should decode translation to your target sentence. And of course, people used the architecture known as an encoder decoder. So you have specific network to encode your input sentence, and like you want to learn good representation of your source language, and you have decoder, and in parameters of decoder, you learn representation of your target language. And then you translate from one to another with this architecture. And the problem here is that you need to compress all your input sequence in source language into the like dense representation, like some vector, which then will be used by decoder to decode, to generate your output sequence. And people try to resolve this problem. And in 2014, group from Montreal, they proposed so-called attention mechanism. How it works. So actually, the idea was that we should create something like retrieval mechanism, which will help us to use not only the last state of our encoder, but to accumulate weighted representations from any element of our input sequence. So the idea was that, for example, if we look at the decoder here, on the last element, we want now to predict a word for these elements. So here it should be hat. I saw a hat. And to do this, what we can do now, we can take this representation, say, and this is like our current state of our translation. Now we want to understand which representations in our input are relevant to the current state. So we introduce some trainable attention function, which has as an input our current state and some state from our history. So it's like, you see, we have all these pairwise comparisons of our current state with every state in our source sentence, so every state of our encoder. After that, as we have this attention function, which is like trainable during training, we hope that it will learn how to score these interactions properly to make translation better. Here, in this example, we see that the word representation for the word cat has highest weight produced by this attention function compared to others. So after we have calculated scores for every pair of elements, now we can just have integral representation of our input sentence, which is specific to our current task of decoding this specific word. So what we do, we just like take all these weights and multiply our input vectors and then just add them all up. So this is idea. It's something like retrieval of information from our memory to create representation which is most useful for our current task. And as I've said, first, this idea was used for machine translation, but in few years, people understood that probably what you can do as well, you can attend not only on the source sentence. If you want to have a language model, only generative model, this decoder part, you can attend also to the previous elements of the sequence. And this is called self-attention. And this is actually the major block of the transformer architecture. So this is how we got these attention mechanisms in AI systems and neural networks. So now let's switch to the transformers. So, who knows then the first transformer paper was published? 17? Actually, when you will be in London, you can go to Royal Institution, and in the basement of the Royal Institution, you might find this like exact physical realization of this illustration from Faraday's paper on ring transformers. And of course, yeah, you are right that the current reincarnation of transformer is 2017. And you see here that the first transformer, it was like you see two parts, one is encoder and one is decoder. But current LLMs, they are all replicate decoder part of transformer architecture without cross attention from decoder to encoder. So let's go through the GPT-2, which is like classical transformer architecture. And actually, all the current large language models, they replicate very, very closely what we will see now. So just like we will go step by step through the forward path of transformer to remind you how it works. So what we have for an input and defining our computation here. So first we have a vocabulary of tokens. You can think of tokens as a subwords. We have, and usually the size of vocabulary from, I don't know, 30,000 to maybe 150,000. And we have some sequence length of our input sequence, which for which we want to predict the next element. And in GPT-2, we have a fixed context length, which is Tmax. And we have, for every element, we have some hidden representation or embedding with dimension D. And we have L layers, H heads, and every head is an attention mechanism we discussed earlier. And why we have multiple heads? Because probably for machine translation, we don't need multiple heads. We always solving the same task. But for language modeling, probably for different tasks, for different situations, for different contexts, we need to pay attention differently to our previous history. So we need to learn multiple attention scoring functions, which will focus on the different, semantically different parts of our input sequence. So we have so-called head dimension, which is usually just dimensionality of our embedding divided by number of heads. We have IDs for our tokens, and then we have token embeddings matrix E and position embeddings E. And what we do, so we have a large vocabulary. And for every word in vocabulary, we want to represent the sequence. So we use one-hot encoding. One-hot encoding is that we just, for if we know for that in this position we have this particular word, then we have the vector which represents this word along the whole vocabulary. And that's it. So in GPT-2, we have learnable token embeddings. So we have this one-hot embedding for your word. And now you have dimensionality of, say, 30,000, and you want to project it to your hidden dimensionality, which is, say, 124. So you use these embedding metrics, which is trainable for this next token prediction task. So you project your one-hot embedding to your dense representation, to your dense token embedding representation. And as well, you do the same for your positional encoding. So for every token, you have one-hot encoding of position, and you have your trainable position encoding matrix. So you just multiply them together to get your positional encoding. And these two vectors, you just add them up for every element, your token embedding and your positional embedding, to have your representation of your, which will be your input to your transformer layers. And of course, usually you do this all in this, like for all elements in parallel. So you have like a pretty large tensor which combines all embeddings together. So now we have all our preparations ready for computations inside transformer layer. And you see it's a bit confusing that usually on these diagrams for transformer, you have input at the bottom and output at the top. But when you have all these line by line descriptions, you are going from top to down. We will have some crisscross errors. So to make computation stable, specifically during training, transformer architectures relies a lot on a layer norm, where you normalize your token representation heavily almost after every transformation. So we take our input representation for the zeroth layer. So first what we do this layer norm transformation. Then we calculate our multi-head attention, and the output of this transformation, we will go into more details on the next slide. But the output has the same dimension as our hidden representation or residual representation here. You see this error, which shows that we have our input vector and we have output of our multi-head attention mechanism, and then just add them together after attention. So in some sense, we steer our hidden representation with the correction produced by our multi-head attention mechanism. After that, we apply a layer norm again, and then we do a multi-layer perceptron plot where we have this vector, and we calculate updates, like extracting some information learned by transformer during pre-training. Then after that, we add this retrieved information from memory to our current state, and we have output of our layer updated representation. And in GPT-2 models, usually there are multiple sizes, but you can imagine that you have like 30 layers for pretty large model and 30 different heads. So let's go into detail how we calculate attention. So as you remember, attention, it's like a pairwise comparison of elements. But here, as we have autoregressive model, usually we cannot look forward into the future. So for every element, we can calculate attention only to the previous elements of the sequence. So to calculate attention, we have like three basic transformations. We want to transform our current representation of the token into the query, keys, and the values. And after that, we use our query part to match our keys with so-called dot product attention, and then normalize it by dimensionality of our head and apply masking here. After we have calculated scores for all pairwise interactions, we then normalize them with the softmax to get final attention scores. Then we use these attention scores to accumulate our value vectors, which we calculated on the previous step, to have output for one attention head. After that, as we have multiple, it's like say 30 heads, and each of them operates in a much smaller subspace, and we just concatenate all of them together and do final linear projection from this concatenated attention output to the output of the whole attention mechanism, and then add our residual stream. And in GPT-2, for this feed-forward network, people used GLU activation. So as you know, actually used multiple other activation functions. And now, in the sake of efficiency, people usually use ReLU, which is even much simple function. But usually it's some nonlinear function which has which is close to 0 if all negative inputs and like linearly scale with positive inputs. After you have repeated this operation for 30 times, then now you are ready to make prediction. Finally, you do layer norm again, and then you calculate logits with some linear mapping, and you do again softmax to normalize your logits into something looking like a probability distribution, and you sample from this probability distribution to predict the next token. So actually, this is basically all the equations you need to calculate forward path of the transformer. And I think it's useful to think, and it's usually represented by this diagram. So you have your input vector, you have this k, q, v. This is why you have these three errors on this diagram. And then you, after calculating this vector, you just add it up your residual representation, and then feed forward, add it again. I found it useful to think of transformer architecture as some kind of cognitive architectures with different kinds of memory. So you can imagine that your residual stream or your vector embedding is some kind of working memory. So you have some state of your memory which you update with every part of your transformer architecture. So multi-head attention, it's like a short-term memory. So you have some context, and you can retrieve from this short-term memory some information. You can, with your attention, you can accumulate this information differently. And after that, given this information, you can update your working memory. You just add your output of your multi-head attention to your working memory. After that, you take this updated memory. For example, you find something useful in your context, and then you need to remember something which is related to this context, which you have seen during pre-training. And this information, this statistics from pre-training, it's stored in the weights of this feed-forward network. You can see that this feed-forward network is some kind of long-term memory. So you retrieve information from your long-term memory, which is relevant to current state of your working memory, and then you update your state of your working memory. So it's something like repetitive. You review your context, retrieve from the long-term memory, review context, retrieve, because you can have like different views on your context depending on what you have retrieved from your long-term memory. Okay, any questions so far?
Sorry, the layered norm you take again and again, is that some kind of a z-score? Because it had like you're subtracting off mean and then you're dividing it with some kind of standard deviation.
Yeah. Okay, so now let's quickly go through the history, how these fancy transformer architectures become transformed into the large language models. So when we started like in the field of natural language processing, we have neural networks or models for every specific task. So if you have to solve like, I don't know, 5 tasks, you for every task, you have your own data, and then you train your model only for this data, and you solve it. At some moment, after the introduction of transformer, people started to train in self-supervised manner language models, but they were not like universal models. They were semi-universal models. So you train encoder model, then you have different downstream tasks like sentiment prediction or predicting next turn in the dialogue or some other task, and you take this larger model, and then you have small amount of annotated data, and you fine-tune this model, like you add specific head and you fine-tune this model to solve this task. But due to the nature of language and why I think that it turned out that LLMs are so powerful, because actually language provides us medium to formulate problem and as well to formulate solution to the problem. So, and if you train the model just to predict the next word in many formulations of the problem and in many reasoning traces and solutions of the problem, then the model will might acquire, and we see that actually this is the case, capabilities to generate solutions for the problems. And this is because like medium for formulating problem and for like solving problem is the same. And another curious fact which contributed to the success of large language models is the neural scaling laws. And you can imagine it in a different, from the different viewpoints, but I like this one the most, is that here you have with a different color, it's a training curves, like loss function given a number of tokens processed during training. And you can see here that in different colors, you have different models with a different number of parameters. And if you fix your token budget, so you have some data set with a limited amount of data. First of all, of course, you see that the more data you have, the better results you get. But the most interestingly, if you fix the data size, then the larger the model, the faster it learns in terms of the number of seen sample, and the better quality it has for the fixed number of data points. And this is what this phenomenon was called neural scaling laws. And actually, all the hype around LLMs, it revolves around this idea that if we throw more compute, we will get better and better, like more parameters, then we will get even better quality. And you see, I was working in natural language processing for the last 10 years. And Transformer was introduced in 2017. And here is a map of large language models before ChatGPT. And you see, I'm sure you never heard about all these large language models. And because actually they were not very useful. As I've said, language modeling, GPT, it takes only decoder part. But for practical applications like filtering out news, predicting sentiment, or something like that, it's better to use encoder, not decoder part, because encoder has bidirectional links. It can calculate interactions between elements in both sides. And so people in real life application used mostly these first encoder part. So what was the problem? And actually, I think that the main problem is in the probabilistic nature of language modeling task. And due to diversity of data we are training on. So if you train on the whole internet, of course, what is happening, and at every time step, you predict probability distribution over tokens. Of course, you have a lot of sequences with similar beginnings, but different continuations. So you have and you have propensity for the model to hallucinate, which means that if you have these, in your training set, you have these 3 sentences, for example, but they are close to each other. So during generation, what you can see that your model jump from one sentence to another, and usually it's between sentences, not inside one sentence. And then you see all these hallucinations because the model has no idea why it should stick to one particular like line of thought. So I think that ChatGPT breakthrough was related to solving this problem. So OpenAI focused on making these probability distribution tailored to the task of making language model helpful to the user. So what they did 2 main things. First of all, they collected some training data where we have simulated dialogue with a human expert, which explains you something or shows you how to solve the problem. And then they, after pre-training on the texts, they just fine-tuned on these specific data traces. thus increasing the probability of the traces, not just general like sequence of sentences from the internet related to your query, but something like selecting out of all this variety of continuations, only these continuations which are relevant for assisting task for the user. But of course, here they found that they had not enough data just for self-supervised fine-tuning. So then they decided that they need more data, and to generate this data, they used reinforcement learning. So they trained the model, which can differentiate like helpful continuation of the dialogue with a non-helpful continuation of the dialogue. And with this model, they were able to get like more data to train the model on and to convert it to what we know ChatGPT. And after ChatGPT was released, of course, people were very fascinated. For example, as I've said, I'm working in NLP from 2015, and then I saw ChatGPT. I can't believe for a couple of weeks that it's possible, because I've used before, I've chatted with a lot of previous ChatGPT models and all like Google models. They were never close to what we have seen from ChatGPT. People, after ChatGPT was released, people started to play and trying, of course, apply it to mathematical problems, starting from very, very simple, because we are always curious, trying to test and break something, the most complex task we can have at hand. And what people found actually, so if you, they started with an approach which is called in context learning, when you provide like your data set in the context of your model. So in your data set might be you have question, you have answer, question, answer, and then you finish your prompt with the question and expect model to generate answer. And what people found that if you provide your examples, not only in the question answer form, but in the form of question, reasoning, and answer, then the model has much higher probability to correctly answer the question. And actually, as we understand now, this is due to the depth of the model. So imagine that here you have some statement of the problem, and here is a like reasoning. You need to solve this problem, and actually LLM, as it is feed-forward architecture, it has constant number of computational steps it can perform to solve the problem, and this number of computational steps is limited by the number of layers in your architecture. And it's very hard for the model to compress like the proper number of computations inside the model, inside the layers it have. And it's much easier, like this reasoning trace provides a way to decompose these computation in smaller chunks. So for every token, you do some part of the calculation using all the budget of your layers. So which means that if you compare left-hand side and right-hand side, then depth number of layers you have used to generate answer increased by the number of tokens multiplied by number of layers in the reasoning, which makes your computation much more expressive. So this is why chain of thought prompting works. And after people discovered this chain of thought prompting phenomenon, they started to train LLMs with these reasoning traces. And probably the first model available was O3 from OpenAI. And at some moment, it was like proprietary stuff, but DeepSeek R1, about a year ago, they published open source another technique which can have the same results. and which solves the problem of collecting reasoning traces, because you need, for your training data, you need to collect a lot of reasoning traces for your problems. And what they suggested, so they say that if you have problems, set of problems where you have verifiable response, so you know the answer, then you can use reinforcement learning to train your model. So your model just generate a lot of reasoning traces, and you can score with your reward function if the answer is correct or not, and then enforce these reasoning traces which are good, and decrease probability for these reasoning traces which are not good. And the key here is that this applies for only for verifiable traces. So if you have some reasoning which is not verifiable formally, then you cannot apply this training method.
Okay. Can you say in this context what is the environment for the reinforcement learning?
So environment is like sequences of tokens.
And
So
you can score in some way, right? You have a
yeah. So usually it's like a high school problem where you have answer at the end, answer 9 or answer 11.
Yeah.
And if you have something else, anything else, your score is 0. If you have correct answer, then your score.
You need some sort of verified set of reasonings.
Yeah. So, but of course here, the good part is that you don't need to verify every step. You only need to know the correct answer. But what is in between might be anything. And you can see here performance on AI, ME data set, which is, I suppose, mathematics and bit mathematical problems data, some mathematical problems data set. But after its training steps, we have this increasing accuracy of the model. But on the other hand, also, if we look at the number of average steps per response, it also grows with the training step. So, which means that for the better quality of solution, the model usually uses more steps, up to 10,000 steps. And this is technique. It has evolved over the last year. So now we have a lot of variations how to make it better. So models becoming better and better at reasoning, and we are starting to use them to solve all these kind of mathematical problems. And so that's it for the part of general LLM history overview. I hope that it was useful. And now I'm switching to the couple of examples of the latest system which use LLMs inside some framework to solve mathematical problems. And the first one is AlphaEvolve. And the idea behind AlphaEvolve is that you want to produce reasoning where every step is verifiable, because then it's easier for you to check the solution. And how we can do this? We can represent the reasoning as a computer code, computer program. And then in this case, it's easier for us to verify the answer and to verify every step. So to check if every step is correct. So, and another idea is that we can treat large language model as some kind of mutation. So it can produce some variation of your existing solution, which might be in the direction you need to solve the problem. So the AlphaEvolve system, it consists of 4 main parts. One part is these LLMs ensemble, which is like a parallel agents working, trying to improve solution. Then you have evaluation component, which evaluates quality of your solutions. Then you have a pool of your programs. It's like a population of your solution, which you can use to generate more solutions. And you have a prompt sampler. It's the thing which can retrieve something from your program database and for generating some parts of your existing solutions to generate new solutions. So how would you use AlphaEvolve? First of all, what you need to do, you need to write some initial program which has probably very crude but correct solution for your problem, maybe not optimal. After that, and this will be your initial, you put your initial program into your program database. After that, you create some template and configuration for the prompt sampler. So it's some selection mechanism which will select the most useful parts from your program database for your next step of generating variations for your solution. So you then step by step, you have your initial set of your programs. You retrieve from this initial set some program, some components. Then you use LLM ensemble and you ask models to read existing solution, to read problem definition, and to generate modification of existing solution, which might improve this solution. So you see here we generate these diffs for existing programs with LLMs. Then with these diffs, we create a child program, and then we evaluate this child program, how it solves our problem, and store this child program and the results of the evaluation in the program database. And AlphaEvolve paper presents results as like solutions for some problems in analysis, geometry, and combinatorics. On the left, you can see short descriptions of these problems. They are mostly related to some optimization problems where you can improve solution to some extent.
Can you say how the evaluation works? Is that something up to the user to say
Yes.
how to evaluate?
Yes. You should write a program which evaluates. So for example, if you, I don't know, you generate some placement of spheres, then you need a code which will calculate some characteristics of this placement you want to optimize. So, and this is, I think that the strong, it's on one hand, it's strong part of this AlphaEvolve solution because everything is in code. So you can easily evaluate, but it's also Do we have any questions from the Zoom? But on the other hand, like programming languages, they are not directly map on mathematical language. So you cannot express all the variety of problems in code. So just very, very recent paper, Aletheia. So anyone knows what Aletheia is? No?
Greek goddess of wisdom or something.
Yeah, a Greek goddess of wisdom or truth. So this is a latest paper from DeepMind. A lot of authors. Demis Hassabis is also a co-author of this paper. Probably he, to his Nobel Prize, he wants to add Fields Medal. Probably Fields Committee might change rules and to award field medals to large groups of authors. I don't know. So what they suggested to do, actually, it's if you look at this diagram, it's pretty natural. So they use 3 different agents which cooperate to solve some mathematical problem. So you have a generator agent which reads the problem and generate candidate solution. Then you have a verifier agent which estimates if this solution is critically flawed, then you need to regenerate it from scratch, or if it needs some minor fixes, and then it sends this solution to reviser, and reviser revise it for candidate solution. And after verify is happy, then you can say this solution is final output of our system. I should stress, it was quite confusing for me to have this part. You see this generator and reviser, the nice classic columns here and the boxed, but verify is some circled thing. And I thought actually that the verify is a formal verifier. Like you have solution, you translate it to lean or any other engine, and then you verify it, and then you can say if it works or not. But if you read the paper more carefully, you found out that the verify is just the same LLM without any formal verification, which they call informal verifier. So it's just the same LLM with a prompt saying verify please this solution. So far so good, which means that basically, and we know this from alpha proof and from all the previous attempts of DeepMind to solve Olympiad problems, that formalizing problems and formalizing solutions is still not solved task in this area. And they tested performance of this system on the Olympiad IMO problems and found that it outperforms normal DeepThink. So this blue line is actually the LLM DeepThink inside this generator, reviser, and verifier. And this red star is how much this overall architecture adds to the solution quality. So you see, this blue line is if you just throw the problem definition in your LLM, how good it's solving problem. And red star here is this whole architecture of free agents, verifier, and blah blah blah. And it's better on IMO and Future Math. And Future Math is some internal data set of Google DeepMind, more complex PhD level exercises. And also they have tried this approach on the problems from the Erdős problems database. So they filtered out 700 open problems from this database, and then applied Aletheas to solutions of all of them. And their verifier estimated that only 200 solutions were correct out of 700. And they took these 200 solutions and verified them by hand by mathematicians. And here are results. So out of these 200, 137 were just fundamentally flawed. 63 technically correct, and 13 meaningfully correct. I don't know what so the difference technically correct, which means that it is not solving problem, but it has a consistent solution probably. So meaningfully correct means that it's consistent and solves the problem. And they report like 6.5%. And I found this figure, actually, this percentage quite confusing because it's 6.5% of 200. But actually, they started with the 700 problems. And actually, this is only 2% of the initial. Okay, so now you see like the current cutting edge results we have in this area. So quick warm up over this LLM part, and I will have 10 minutes to finalize with long context stuff. So LLMs are just neural networks trained to predict next element in some sequence, natural language or coding or mathematical reasoning. Majority of LLMs use transformer as a backbone. Transformer has 3 types of memory: attention for short-term memory, feed-forward or MLP for long-term memory, and working memory is or your token embedding. And training of LLM is a multi-stage process where you have first pre-training on just texts predicting next token, then you have post-training where you train on the sequences which are most relevant to your task at hand, for example, to be assistive. Then you have post-training where you can even like make more specific like reasoning traces for your task and reasoning post-training. And LLMs can solve IMO level problems and becoming helpful in mathematics research. But still, what we see, and this is one of the questions I'm curious, and I'm sometimes asking people who are working on reasoning in large language models, is that now these models can solve IMO, but if you provide these models with a very long context, they still start to hallucinate, and they lose the ability to solve the problem. So in some sense, we see that this capability is translating not very good, even in some very common sense domains. Here, for example, results from our paper on benchmarking simple reasoning in LLMs. So what we did, we take very simple reasoning tasks. You have some persons, they are located in some rooms, they move between rooms and move some objects with them. For example, John went to the kitchen, Mary went to the bathroom, Eddie went to the garden. And you have like 10 facts, and you have millions of tokens, and you put these facts inside these millions of tokens and ask, where is Mary? It's the simplest problem. And you can see what is happening with current frontier models on this task. So this is only, you have 10 facts and you need to answer the question at the end. And here is a context size. And you see that for like small context size, if you have only 1,000 tokens, you can have very high performance. But if you have 100,000 tokens, which is 10% of million context window, then you have troubles with predicting this. And if you need, if you just make task a bit complex, you need 2 facts, for example. So in first fact, you are saying Mary pick up the ball. Then you have like, I don't know, couple of books. Then you have sentence, Mary went to the kitchen. And then at the end, you ask, where is the ball? So to answer this question, you need to combine both facts, that Mary picked up the ball and that Mary traveled to the kitchen. So you cannot solve this problem by any of these facts independently. And you will see that you have much worse picture. Model scales with the context size badly. If you have 3 supporting facts, then it's just disastrous. And it's for me, it's puzzling why models, they are so good at like complex problems, but they still, with even simple facts, it's hard for them to filter out relevant information from irrelevant, from noise. And practical outcome of this, when you put your mathematical problems in prompt, and after the model generated a number of attempts to solve it, you can say that your context, and you have no solution yet, then your context is poisoned. You need to like keep only the things which you think relevant for your future attempts, then just throw out everything. You should not add more and more and more, because you see the quality of your solution like degrades. So what we did a very stupid thing. We take a transformer and hypothesized that probably we can combine power of transformer in a local window with the good capabilities of recurrent models for the longer sequences. So we created architecture which we have named recurrent memory transformer, and the idea is very simple. So if you look at it as in an encoder implementation, so you have a very long sequence, 1 million tokens. You split it on segments, say 1,000 tokens. And for every segment, you add special service mem tokens, which has no semantic meaning by themselves. But then you fine-tune your model to process the whole sequence. This segment prepended with the memory tokens to generate output for context as well as for memory. And then you take these outputs, hidden representations of your memory from the last layer, and feed them in as an input for the next segment, which means that the model can learn to store information which is important for your task in representations of these memory tokens, because you carry over for the next segment, and so on and so forth. So we effectively provide some kind of episodic memory to our model. And what we found, actually, we were very surprised in our experiments. So we used curriculum learning to train our model. So we first started with the first segment with this single fact question answering task. And you see that the model was able to solve it with 100% accuracy. But if you test the model trained on only one segment, then it cannot generalize to more segments. Like if you test this model on 2, 3, 4, it like have chance level probability to answer the question. So if you train the model on 2 segments, so it learned how to carry over information from the first segment to the second segment, you will see that it is able to generalize to solve the problem for 3 segments as well, even if it never seen 3 segments during training. But then this quality degrades pretty quickly when you add more and more segments. But if you continue training, so you take this model trained on 2 segments and train on 3, you will get even better generalizability. If you continue up to 7 segments, at some moment it starts to keep performance very well. So it starts to generalize very well. When we have seen these results, we were actually very happy, and we just started to hear like a number of segments. We started to test the model on more and more segments. And at the beginning, we saw that you see these declining curves here. So this is starting tests. So we expected that something like this, and the quality will go gradually with the number of segments lower and lower and lower. But we've seen something like this. So after this first initial period, our accuracy just stayed flat. We are very happy with this. And when you see here is a logarithmic scale, you add more and more, and it's still the same quality. We were very excited and started to at this moment. And when we finished our draft, we already have twice more length and still good quality. And then we improved this architecture, but I have not that much time to explain it in details. So to our recurrent memory tokens, we added also like something close to the state space model, some associative memory for every layer, which helps a model to keep better representation and translate it to every token representations inside in context. And here are our final results. So with this, we were able to scale the model with a recurrent memory transformer. We have like about 80% accuracy on 10 million tokens. And with this associative recurrent memory, 80% accuracy on 50 million tokens, which is actually today, I have never seen any paper which claim that they solved any task on more than 10 millions. So this is like still the world record for the longest sequence processed by any transformer. And here are performance for other tasks as well, 2 supporting facts, 3 supporting facts. And so you see this architecture is better than Mamba, so state space models or any other models on these tasks. But this recurrent memory provides not only storage for the information, but also a way to extend the depth of the architecture. So if you imagine your memory vectors with every segment, it's like you add more and more layers on top of your computation. And so we tested on the simple toy problem where you have a sequence of elements and each element should be labeled with the product of all previous elements for specific groups. And you can see here, for example, that for Z60 transformer and recurrent architectures, they perform the same and they have good scaling. So here we have number of layers required to solve this problem. Here is the length of the sequence. So they solve this problem for any length with just 2 layers. But if you go to more complex problems, for example, for A5, then you will see that transformer needs more and more layers as well as Mamba to solve this task. But LSTM, simple recurrent architecture, only 1 layer, and our recurrent transformer needs 2 layers. That's the architecture. So because it can update some state which is carried over for further elements. So conclusions: recurrent memory transformer extend effective context for very long sequences, and associative recurrent memory transformer is even better. But we still not yet here. But for scaling these architectures to general purpose tasks, we can apply them only to some specific tasks by fine-tuning these architectures on this stuff. Well, thank you for your attention.
Alan just had to run off the chair, so I think we are running a little bit over. Just any one question, maybe, before we move on.
I will be available.
I just have, okay, I'll ask one very silly question. You had a list of Erdos problems. Some of them you said were like trivial or like proven, and some were faulty. Was there any like relationship between the ones that were faulty?
I don't know. I didn't find any analysis of why faulty, yes, no faulty problems in the paper.
Okay, then next up we have Finn and Ryan giving us our tutorial on LLMs. So Challenger sent me a little introduction, so while Ryan is getting set up. So Ryan is a senior machine learning engineer with Accelerate program, scientific discovery at Cambridge University, and is interested in scientific research which is grounded in excellent software engineering and machine learning fundamentals. For working Accelerate, Ryan's research interests explored unconventional approaches to computing in complex physical devices in the world of condensed matter. And Ryan has been instrumental in conducting numerous workshops around the university, empowering researchers and industry practice machine learning tools. So that, Ryan.